Okay, so for this one here, this is again an unbounded integral. We are going to, now let's just quickly sketch this graph so we have a good idea what it looks like. It's got a vertical asymptote here, and as it approaches, it's going to go like that and like that. Okay? And we're integrating from -1 to 5. So we're going to integrate this side all the way to x equals 5. Okay, so that's the area that we're looking for. It's unbounded at -1. So we have to write this as a limit as a goes to -1, and that's from the positive side of the integral of a to 5, 1 over cube root x plus 1 dx. Okay, so I'm going to undo this integral, so it's going to be, let's see here, limit as a goes to -1 from the positive side, x plus 1 to the power 2/3, and then divide by 2/3, I can get 3 over 2, and that's from a to 5. Okay, so I can plug that in. I'm going to end up with, what is that going to be? Plugging in 5, I get 6, so 3 over 2 times 6 to the 2/3 minus, when I plug in the -1 in there, I get 0 to the power 2/3. Okay, that's going to just be 0, so I just need to work out 6 to the 2/3. It's going to be 3.03, and then I'm going to times that by 3 divided by 2. Okay, so I get a total area of 4.95 about units squared. Okay, this is an unbounded area. I'm going to just sketch that in. It's going to be e to the x, and it's going to go from 2 to infinity. Well, we know that area is infinite. We need to still use a limit. Limit as a goes to infinity of 2 to a e to the x dx. This becomes limit as a goes to infinity, e to the x from 2 to a. And so we end up with e to the infinity. That looks like infinity, but I'm just going to change that. A e to the infinity minus e squared. Well, that's going to be infinite area. Okay, and that's clearly going to be the case. Differential equations. Okay, to be able to solve differential equations like this, these are implicit functions. We have to be able to split it up with times and divide. So we need to be able to get the y to that side by multiplication or division, and dx to that side the same. So when I put the variables with the dy, the y variable with the dy, I get that. And I get sine x dx. Okay, that's really secant squared y dy is equal to sine x dx. Well, I can integrate both sides, and this is a standard integral, and this is a standard integral as well. Okay, so there's my implicit function. I can solve for c by plugging in, and I'm going to end up with tan of pi over 4 is equal to negative cosine, or I'll just go plus cosine of pi over 2, which is 0, is equal to c. That's going to be tan of pi over 4. The tan of 45 degrees is 1. 1 plus 0 equals c. So c equals 1. So my equation implicitly looks like this. Tan of y equals 1 minus cosine x. If I want to write this in terms of y, it's going to be the arctan of 1 minus cos x. Okay, there it is. And I've solved for c because I have the initial condition.